In the previous video, I talked about the first part of the neopixel circuit and the most important part, which is the master clock. And so here's the schematic of how the master clock is hooked up. The master clock is an 800 kilohertz signal, and that is going to a bunch of counters. These are CD 4017 counters that count up to the total number of bits in all the neopixels. And through a series of AND gates, they trigger a monostable 555 timer that puts out a 340 microsecond, has to be at least 250 microsecond low pulse. Well, it's a high pulse that's inverted into a low pulse, and that stops the clock. It also resets the counters. So in this video, we're going to talk about the next part of the circuit, which is the D flip-flop. And if I get to the monostable pulse generators, then that's what I'll do. And so the D flip-flop, the purpose of the D flip-flop here, as we discussed in the first video, is basically to synchronize all the pulses together in order to create a nice synchronized output to the neopixels, and it allows for the data in. So now we are going to talk about the D flip-flop now. So we have our master clock input, and that's going to be our clock for the D flip-flop. For the flip-flop, I use the let me increase this a little bit. I used a 74HC74, which is a dual D flip-flop. It's got a flip-flop on one side and a flip-flop on the other side. And basically, what a D flip-flop does is a D flip-flop allows data, which is the D, to be clocked in with a clock pulse, similar to the way it's used on a computer. So the master clock, which is an 800 kilohertz signal, and the duty cycle on that signal is fairly large. It's about 80 to 90% duty cycle. And the reasons for that, as we discussed in the first videos, so that when the end happens with the low and high signals, it's the positive part of the duty cycle is long enough that it'll encompass the entire monostable high pulse, and it's definitely long enough for the low pulse. So when we have that master clock, that goes to the clock input of the CD4017 flip-flop. So I'm going to draw the flip-flop the way it's usually drawn, where there's a VCC and there's a ground for the chip itself. Then there's a Q output and a Q bar, which is the inverse output. So this is the clock, and this is the data input. So the data input goes to pin 2. The clock goes to pin 3. The Q is pin 6. And the Q bar is pin 7. Ground is pin 8. The VCC is pin 16. And there's two additional inputs to this flip-flop, which are the preset and clear. And these are active low. So the preset is basically equivalent to the set of a conventional SR latch. So I'm going to draw those out here. So pre and clear. And the reason why I make note of these is because I'm going to use them later for the pulse generators. But basically, the way this works is these both have to be wired together and to VCC. Since they're active low, we don't want them presetting and clearing asynchronously. We want all the data to be coming in from the data input. This is once again, our master block diagram. And you can see here, the data input goes in here, and that's our flip-flop. And that is all there is to it with the Q and Q bar. So when the data input is a 1, the Q goes to a 1. When the data input is a 0, Q is 0 and Q bar is 1, and so on and so forth. These outputs basically are, let me separate them a little bit. And I am going to bring in this AND gate. And so you could use an AND gate for this. I actually used transistors for this, but, and I'm going to draw both circuits, but if you were going to use the AND gate, you would put the high pulse here, and you would put the low pulse here. And so if this output is a 1, this will activate this AND gate with the high pulse, which is coming in synchronized with the master clock. And if the output was a 0, then Q bar would be high, and this AND gate would be activated, and it would provide, it would AND with the low pulse. So the output from this would either be the high pulse, which when we talked about in the first video, is an 800 nanosecond, 800 to 850 nanosecond pulse, which basically is the high pulse, which is 800 nanoseconds, ANDed with the clock pulse, which is longer than 800 nanoseconds. And when you AND these things together, you get this pulse, the high pulse. Similarly, the low pulse is made in the same way. The low pulse is approximately 400 nanoseconds. And when you AND it with the clock pulse, which is significantly higher than that, you get the low pulse. And so the output of this one would be this. But it will only produce this pulse if the Q bar is high, meaning that the data input is a 0. So now, based on that, those get placed through an OR gate, and this is an OR gate. So either this or this go through, and that goes out to the neopixel strip. All right. So these could be done with the AND gate, such as this, and these could be done with a separate OR gate. At the time when I was building the circuit, I did not have these chips, and I did not have these chips, which I still don't have, actually. So the way I did the AND gate is different. I made the AND gate using transistors. And so the way I did that was basically the circuit is fairly simple. Transistor AND gate. The way you make it is you basically have to have two transistors, two NPN transistors. I had two N2222s. This goes to VCC. This goes to another 2N2222 transistor, and a 100K resistor to ground. The inputs of this are taken through a high-ish value resistor. And this is, and the output gets taken from here. So this is, if you were going to use the AND gate, AND gate schematic here, basically the A input is here and the B input is here. And when this transistor, and the way it works as an AND gate, is you do not have any conduction going through here at all if the A input and B input are off. Once the A input goes on, this transistor will conduct, but if the B input is off, the current will not flow beyond this point. If the B input is on alone, there will be no current flowing down here. If both A and B are on, then this will output. This will both of these transistors will conduct, and the current will make it all the way over here, minus the 100K resistor. So the path of least resistance will be to the output, and the output is where you get your AND gate signal. And it works beautifully in this situation. And so I have both the high pulse ended with the Q and the low pulse ended with the Q bar. And I did this with 4 total transistors. And then I made an OR gate using a simple, even simpler circuit. Basically, I used diodes. And so input A, input B, and then I connected those together. I had a 1K resistor to ground here, and this is the output. And basically the way this works is, if you're looking at this part of the circuit, after this, you either have a high pulse coming in or a low pulse coming in, but one of those, and that's based on the data in. And so either of those has to go through here, and this output goes to the neopixels. And so either of those goes through here. But when, let's say, the A output is on and the B output is off, you don't want the A current to go through the diode and go back to B. you want it to all go forward. So that's the purpose of this diode here, and similarly, that's the purpose of the A diode, because you don't want the you don't want the current diving back and being sunk into the AND gates here. And so the way this works is if either A or B are on, and the way this circuit is built, either A or B are on. You can never have a high pulse and a low pulse at the same time, because Q is either on or off, and Q bar is either off or on at the same time. And so either of these will go through the OR gate and then go to the output. And that's, a simple way of making an OR gate. If you have two diodes, and you don't have to open a whole or get a whole nother chip to do this. And so that is how we get our finalized signal output to the neopixels. As long as you continue to have the clock running and whatever data you have. Let's say the data pin is not connected to anything and it's just 0. If the data input is 0, then Q bar will always be on, and this will continue to send low pulses. And if it continues to send low pulses, they'll transmit through this OR gate and go to the neopixels. And every time the neopixels refresh, or based on the counter, they are going to be all off. Similarly, as after you get a 1 here, the Q will go high and the Q bar will go low. And so this AND gate will be off, but this one will be on. It'll produce a high pulse, an 800 nanosecond pulse, which will go through the OR gate and to the neopixels, and will turn it on every time there's a value of 1. So in a way, this D flip-flop is basically a translator of zeros to ones, zeros and ones, and zeros and ones are translated to a high pulse or a low pulse. And that's how that portion of the signal works. In the next video, I'm going to talk about my trials and tribulations with generating these high and low pulses using monostable pulse generators as they are triggered by the clock. We're going to go over these last two parts of the circuit, which are going to these AND gates, and how to generate a stable and synchronized simultaneous high and low pulses every time on every pulsation of the clock. So as always, thanks for watching, and I hope you stay tuned for the next one.